So good morning, everyone. I'm Andrew. I'm a PhD student at the University of Oxford. And today I'll be giving a presentation about my research, which focuses on the performance of large offshore wind farms and about how we use machine learning to improve the predictions of wind farm performance. And specifically, we use the technique called multi-fidelity Gaussian process regression, which I'll explain a bit more later on in the talk as well. So my supervisors are Takafumi Nishino from the University of Oxford and Tom Dunstan from the UK Met Office. And we've had help from Francois-Xavier Briel from UCL as well. So to give a bit of background, the total installed capacity of wind energy is projected to increase rapidly in the next few decades. So as an example, the UK has a target by 2030 to increase its capacity of offshore wind energy by a factor of 5. So in order to achieve these targets, we're going to have to design and build very large wind farms in the future. And a key aspect of this design process is being able to predict the power produced by our wind farms for different designs of wind farms. And for this, it's important to be able to predict how turbines interact with each other within a wind farm, as shown by this picture. So these interactions between turbines can impact the power produced by a wind farm by up to 40%. So they're really significant, and it's really important to be able to model these interactions accurately. But the problem is that the existing models used by the wind energy industry struggle to capture these interactions accurately, especially for large wind farms, which are likely to exist in the future. And the reason for this is that it's very difficult to model wind farm aerodynamics generally. So to do this, we have to understand and model complex flow interactions across a really wide range of scales. So the range of relevant scales we have to consider is roughly 10 orders of magnitude. And that means that it's too expensive to simulate everything every time we want to predict wind farm performance. So one approach to this problem is to split the multi-scale problem up with the assumption of scale separation. So we can split it into separate internal and external subproblems. So the internal problem models the aerodynamics of individual turbines and also the interactions between turbines in the wind farm, so these turbine wake interactions. Whereas the external problem describes the large-scale atmospheric response to the wind farm. So today I'm going to be talking about the internal problem because we're trying to better predict the interactions between turbines in our wind farms. So a key parameter for the internal problem is the internal turbine thrust coefficient. And this is used to calculate the turbine drag. And this is important because for large wind farms, most of the wind farm drag comes from the turbine thrust. So this parameter predicts how the turbine thrust changes with wind speed within our wind farm. So here, Ti is the thrust of each turbine, UF is the wind speed within the wind farm, and A is the area covered by the turbine blades as it rotates. So this parameter is key to understand the atmospheric response to our large wind farms. And this picture shows the wind speed simulated within a wind farm. So this allows us to kind of visualize and understand the interactions between the turbines. So you can see that behind each turbine, there's a region with a slow wind speed, shown by the blue regions, and this is known as the turbine wakes. And when the turbine is in the wake of an upstream turbine, then it will experience a lower wind speed, and so produce less thrust. And from our equation for CT star, when it produces less thrust, we'll have a lower CT star value. So we know that this important parameter, CT star, will vary with the layout of our turbines within the wind farm. But there's an existing model for CT star, which is a function of the turbine induction factor only. So this turbine induction factor describes the turbine operating conditions. So here UT is the velocity at each turbine, and UF is the wind speed within the wind farm. So this existing model for CT star is dependent only on the turbine operating conditions and independent of the turbine layout. But we know that CT star is going to vary a lot with turbine layout as well. So the goal of this research is to create a model for CT star, which takes into account these turbine wake interactions, so which depends on the layout of the turbines in our wind farm. And we've used a data-driven approach to modeling these turbine wake interactions. So this picture shows an example layout of a wind farm viewed from above. So we're trying to model CT star as a function of 3 parameters, which describe the layout of our turbines. We have Sx, the distance between turbines in the x direction, Sy, the distance between turbines in the y direction, and then theta, which is the wind direction relative to the x direction. And one thing to note as well is that the turbines are always rotated to face the wind direction as well. So yeah, the goal of this research is to build a data-driven model to describe this relationship between CT star, Sx, Sy, and theta. And we can calculate CT star using a couple of computer codes. So firstly, we can use engineering wake models, and this is used by the wind energy industry to predict wind farm performance. So these models are very quick. You can estimate wind farm performance in less than a minute, but it's not very accurate. So these models work by having a simple model for the wake behind a single turbine, and then simply adding these wakes together to then model an entire wind farm. So this is kind of a very simple heuristic to predict wind farm performance, but it's not that accurate, and it's likely to be less accurate as we build larger wind farms in the future as well. And then an alternative computer code we can use is a computational fluid dynamics technique called large eddy simulations. So these simulations are more accurate because it resolves some of the turbulence, but it's much more expensive. So each evaluation would cost typically 250 CPU hours. So it's too expensive to be used to design a wind farm where we'd have to consider thousands of different turbine layouts and combinations of wind directions and wind speeds as well. So we have 2 potential sources of data to build a data-driven model of CT star. We have the LES and the engineering wake models. So if we built our data-driven model using data from large eddy simulations, we would have the individual data points would be accurate, but because it's expensive to evaluate, we'd have a low number of training points. And this low number of training points may ultimately limit model accuracy. Alternatively, we could train our model using wake model simulations. So we'd have a high number of training points because it's very cheap to evaluate, but the low accuracy of each data point might ultimately limit the accuracy of the model as well. So by using a multi-fidelity Gaussian process regression, we can combine the data sources from different fidelities to create a more accurate model. So for the high, we can benefit from the high accuracy of the large eddy simulations, and also we can benefit from the high number of wake model simulations as well at the same time. And we combine the data using an information fusion algorithm. So just to show this, I've got a very simple example of a Gaussian process regression. So in this example, the solid red line is the function that we're trying to learn. The red circles are the observations, and the dashed red line is our learned Gaussian process model. So you can see that it's not a good model of the true function, and that's because we have relatively few training points. And then we can compare this with the multi-fidelity approach, where we model both fidelities at the same time. So the blue solid line is our toy low fidelity function, which is a cheap approximation of our true high fidelity function. So some of the features are captured in this low fidelity model, but it's not very accurate. But we can benefit because we have more observations of this low fidelity model because it's cheaper to evaluate. And you can see that in the end, we get a more accurate model of the high fidelity function by including the information from the low fidelity model as well. So the information fusion algorithm works by firstly building a model of the low fidelity function, G-low, and then the output of this Gaussian process is then the input to another Gaussian process, rho, which models the relationship between the low and the high fidelity functions. And then delta is a Gaussian process modeling the residual as well. So when we compare it to the results of a standard Gaussian process, we get a more accurate model, but we also get reduced uncertainty in our predictions as well. So information about in this example, the periodicity has been passed up from the low fidelity model up to the high fidelity model. And close to the high fidelity points, the model relies more on those observations. And then far away from the high fidelity observations, we rely more on the information that we've learned from the low fidelity model as well. So just as a recap, we are trying to build a function of CT star as a function of 3 parameters, which describe the layout of our wind farm. So we built a model using a multi-fidelity Gaussian process regression, using a combination of high fidelity and low fidelity data. So for the high fidelity data, we used large eddy simulations, and we had 50 training points. And then for the low fidelity model, we used engineering wake model simulations, and we had 500 training points for this. And then to estimate the test accuracy, we performed leave one out cross-validation as well. For our multi-fidelity Gaussian process model, we had a mean error of less than 1% and a maximum error of less than 4%. And then we can compare this with the existing models to give us a baseline performance as well. So we can compare this with the existing analytical model of CT star. So you can see that the average error has been reduced from over 5% to less than 1%, and the maximum error has been reduced from over 20% to less than 4%. And then we can compare it with the results from just the engineering wave model as well, and we see a similar result. So we've reduced the mean error and the maximum error as well. And then we can visualize the errors of each model using just a simple box plot. So here, MFGP and low 500 is our multi-fidelity Gaussian process model that we built. So you can see that the multi-fidelity Gaussian process model has no bias, whereas the wake model and the analytical model both have a bias for over-prediction. So they're too optimistic for wind farm performance. And the multi-fidelity Gaussian process model that we've developed is much more accurate than either approach. So to conclude, the turbine-wake interactions within a wind farm can impact wind farm performance by up to 40%. And this can be modeled using a parameter CT star, the internal turbine thrust coefficient. And we built a data-driven model of CT star as a function of turbine layout. And we built this model using a multi-fidelity Gaussian process regression, combining data from low fidelity and high fidelity sources. And we had an estimated test error of less than 1%, which was a substantial improvement compared to existing models as well. So yeah, thanks for your attention. And if you have any questions, I'll be happy to answer as well.
Thanks a lot, Andrew. Did you make any modeling assumptions for your residual Gaussian process, that delta term? And do you have like a plot to show how it works? Because if you include that term, you're sort of getting rid of a lot of the bias anyway. So you're to some extent expecting your fitted model to work well, because that should encapsulate all of your bias. So do you have any plots to show specifically that delta term?
I don't have any plots specifically for that delta sum. I think for the implementation, we use the package called MU-Kit, which I think for that implementation, you assume that this residual is independent of the other Gaussian processes, and then you can combine them into one. But if you want, I can share with you the paper, which gives you more details about the implementation.
Any other questions for Andrew? Okay, then thank Andrew once more, and we have the tea at our side. As you use more and more of those expensive models of later.
Sorry, Anna needs to get into the room to.
64. I think you need to. It'll also decrease more, right? If you use more of the.
Yeah, you can add more values to it and make it more accurate if you wanted to as well.
Nice. Thanks. You don't have your slides up there.
Do you want them by email? Is it Google?
Just send me by.
Or do you want a PDF?
Yeah, I think maybe PDF would be easier here. You can also, basically, I just need it in that computer if you have a memory stick, or just send me by email. Then I'll just put it there. Okay.
How much you for any particular bill, basically, but the way you want to do it, sort of reverse engineering, so that you want the to be more close to zero, and then you can use those assumptions of the preference and try and fit the best parameters to fit the best data. So it's trying to work backwards rather than just playing it through. It's a big problem, really, with the whole simulation architecture. Most people don't do it well, but it's something to consider. I'd be interested to see it. Yeah.
So I think there was like modeling the relationship between the different parameters.
Yeah.
I think it's as a function of space, but also as a function of the values.
Yeah.
Then I think maybe there's like some differences that can't be explained just by that relationship. So I think that the residuals and everything else is one. This is the space.
Thank you.
My name is Ron Tyler here for should actually just a quick everything is like the statistical methodology very nicely and I was just wondering, it seems still very clunky to me to set up this really elaborate multi-level Bayesian relation. I mean, probably potentially possible, but still you have to set it up as well. Maybe don't. But I was just wondering, do you think there could be a way to cross-grain to represent these computation results in a nicer way, so in a more physicsy way, where you cross-grain, say, molecular interaction by just tabling, for example, for your free energy functions. Do you have any physics background?
A little bit like A-level physics.
Okay, but I mean, it's quite common, yeah, that you have complicated systems with lots and lots of internal degrees of freedom.
Yeah.
And then you actually account for the effective response of these systems by writing down free energy. I mean, it's the sort of in the physics literature they call it free because it's sort of the output of this the available energy. That's the reason why they call it. Of course, in this case, it's energy production, so it would be it would be much a kind of different concept. But so what I thought is, you see, you have all these turbines, and then you have these weight models, and they just add the weights. Right? And you're basically saying this is probably too pessimistic because I mean, especially if you have a big array of these turbines.
Yeah.
Right. Then you add lots and lots of weights on top of each other that may actually be very inaccurate.
Yeah, I mean, at one point they found that it was completely negative on this.
Yeah,
So they decided to change it.
Exactly. So the point is that basically it's not completely ignores the interaction. That's absolutely fine. I understand. I thought, so maybe once you settle for some sort of geometry, right? So you think of your wind turbines as a blob or so as droplets. Yeah.
Yeah.
So you treat it more like a continuum. Yeah.
Yeah.
Then you could then, for example, compute efficiencies, density, or something like this. Right.
Yeah. I think a slight problem with that is you have it as continuous, then you sort of neglect these. I think from understanding what you're saying, kind of neglect these interactions between the turbines, right?
Yeah. But there would be the effective quantity. Okay, so if you use the model that you used, you then say, okay, so we have a continuum of wind turbines. Okay, and now we discretize this continuum. We look at little squares where everything is homogeneous, and for this square we compute the power output by using your model. Right? The power output for a square then is determined by density of turbines in that square, right? And say some geometric factors like periodicity and so on, right?
Yeah.
Things like this. So that you could then have I mean, basically publish so this could be read by a human, okay? You could then just explain how you could basically create a model, okay? And that could be then simulated with tabulated parameters, okay, which came from your simulations.
Okay.
But then once you've got these parameters, you can then simulate other geometries quite easily, quite cheaply.
Yeah. So I think.
Yeah, you understand what I mean?
I think I can understand what you're saying. I think the problem is like we don't know what these parameters are. So we don't know if it's like average turbine distance in this direction or that direction, but
you could, for example, just play with a couple of parameters. Okay?
People have done this.
And then say what are the most important ones, and just use those.
Yeah. People have done this. So they've done like the average distance of one turbine behind the other, maybe like how much they're overlapping behind each other as well, and it is kind of a little bit better.
Yeah.
But again, I think the problem is like how well this generalizes to. I think that's like even more like abstract data.
Just the session starts before and that should be fine.
Yeah, you've made these parameters.
I've corrected my slide.
Some data
Actually,
based on these different combinations.
Yeah.
That's it. But actually.
Yeah, I don't know how would you ever be able to.
It's a bit more complicated than that.
Into the space.
I didn't really talk about it too much in this talk as well, but like one key aspect to these interactions between the turbines is for the power production or how much they get in the way of each other. But it's also how much that then affects the atmospheric response to the wind farm as well, because if they get in the way of each other more, they produce less first, and then they slow the atmosphere down less. So it's like a balance between.
That's another kettle of fish in there. But I mean that would again fit perfectly well into this kind of physics way of thinking, because this is actually what physics studies does. So you just have compartmentalize, and then you just have some kind of interactions between different scales.
So
I mean the only idea that I suggest is that once you have scale separation, right, that usually allow you to come up with something explicit. That's not only statements. Okay.
Yeah.
So as soon as you have many wind turbines, okay, then it should be. I mean, then basically you separate the scale of the individual wind turbines from sort of from the wind farm scale.
Exactly.
And that's usually that.
I mean,
that is usually exploited.
Yeah, I think like people are trying to, but for these interactions between turbines, the only way people have done is these wave models.
I understand, but I thought maybe there's a what can.
So you think like replacing the statistical model with just a
table.
physical
Table. Yeah. So this is what I'm saying. Yeah. So instead of saying I mean basically you tell the wind farm producers or whatever these people are. Okay. So you tell the users use this model. Okay. So you use the code. Okay. Input your the positions of your individual turbines, and then use the output. Fine. Okay. I mean, no one is against that, but it's still quite clunky and not very intuitive. So basically, if you do this and you want to then design your wind farm, it's very computational, right? Because it's so black boxy, you don't understand what's actually going on. Okay, so you then have to run an optimization algorithm. I mean, you then design your wind farm using some optimization algorithm that uses the output of this multi-level model as an input. Fine, you can do that. But humans typically don't think in this way. Okay?
I see what you mean.
So if you have instead something which exploits the fact that we are talking about some sort of extended region, that might be easier to.
I think that's to work with a different approach, but this one limitation of this approach is that you're limited to having a layout of turbines which is just in this grid fashion, which can only be described by these three parameters, whereas in reality you might have a more complicated layout as well. Exactly. But I think then there's still an open question. If you have a random layout of turbines.
So these large AD simulations don't deal with random placements?
Yeah, they do.
They do?
They're just expensive. They're really expensive.
250 hours. I understand you said so. No, I think it's absolutely fine. I'm just saying you could then try a random by just for some point or whatever, or something like this, and then tabulate that, right?
Yeah.
So I mean,
so I just tabulate a random layout.
Use that. So sort of don't redo all these calculations. So it would be nice if we had a little library where we can just look it up instead of. So then all I'm saying is that this library then should be organized, and the table should be organized in a nice way that we can.
I mean, how do you organize the table?
Well, you would then say, I mean, first of all, normalize it according to things like density, right? How many per square kilometer or something like this. And then there should be geometric factors, like, how periodic it is. You know, I mean, there's a measurement. I think the measurement of that. I don't know. I haven't thought about it.
I mean, maybe there are like some ways, like some parameters where you can capture like most important information about the layout and
Exactly.
add more parameters, and then you can get more detailed information.
Exactly.
About it.
Exactly. So
Maybe there's
that
some way that you can find out.
I mean, I think that would actually make an impact. I mean, I think that would actually be quite
Do you know how
interesting.
to do that?
Well, one would have to start thinking about it, but I mean, I don't know. So normally normally practitioners have a very good idea of usually talk to these people.
Yeah.
And ask them what's actually what's the design process like? Yeah. So how do you go about estimating the number of wind turbines per square kilometer or something like that that you would like to place? And so on, right? And so how important, I mean, how do you think about the boundaries? Like, I mean, is it important that you have a long stretch, rectangular stretch, or maybe a square stretch, square geometry, right? Does this matter? And so on. So surely people actually know the thing to do. And then you have lots and lots of empirical measurements, right? So you actually have ton of wind farms which are operating these days.
Yeah.
You can then also use that data to. I think it's a very cool. It's a very cool question to ask. And,
I mean, it's definitely.
And I really, I really think it's.
I think also this is like this big difference between the two approaches is that like engineering weight models, they have these weights together, and then therefore they could do anything they want.
Yeah.
Which makes sense, but then
Sure. But they don't predict. They're not predictive, and I'm sure that people are actually aware of that.
Yeah.
This happens all the time. I mean, I've worked quite a bit with industry, so they always have this. They have different pressures if you compare with academia. Okay, so for them, the pressure is not so much to publish something, so they don't care, but they have very limited budgets. Yeah, so they can only spend X hours on this, and then they just use any kind of model that's available, but they know these models are not great.
I think they're just tools, aren't they?
They're just tools, yeah. So they know that these models only get them somewhere. Okay? But and then it's just a sort of iterative process. Then they try to get much more accurate information. But ultimately, this is always driven by budget constraints. How much time they can actually.
Do you think like the black box approach is funky just because there's no like understanding?
Yeah. That is my contention. And it's not meant as a criticism.
No.
I'm just urging you to think about what happens at the end. Yeah, sort of. I mean, I think what you're doing is completely positive. Okay, it's really helpful. It's a real. I just at the moment see that this will be picked up by a wind farm designer because they have